So the next talk is LLMs Interleaving Large Language Model for Compiler Testing. Yunbo Ni is going to give a talk.
Okay, thanks for the introduction. Hi everyone, I'm Yunbo Ni, a first-year PhD student at the Chinese University of Hong Kong. Today I'm excited to present our work, Interleaving Large Language Models for Compiler Testing, in collaboration with my advisor, Professor Shaohua. Currently, we have several amazing LLM-based testing tools, such as FastForAll and YFox. These tools have demonstrated great potential in testing with LLMs. However, they are not so effective for testing compilers. If we take a closer look at their reported bugs, two main issues appear. The first one is the low complexity of the generated programs. For example, FastForAll only discovered 8 front-end bugs in GCC. The second is the limited symptoms of discovered bugs. The 2 bugs found by YFox were simple crash cases. This raises a key question. Can today's LLM-driven testing frameworks really hold up in the wild, like in a CI pipeline? There are 2 major challenges to achieving this. First, the typical workflow of these tools feeds code or documents into an LLM and asks it to generate a single test case. To produce millions of test cases, we have to query the LLM million times, which quickly becomes very expensive. Second, the generated programs are often of low quality. LLM tend to produce code with syntax or semantic errors, and even when it compiles, the programs are usually too simple to trigger deep or meaningful compiler bugs. Thus, simply prompting LLMs doesn't mean effective testing, so why aren't they enough for compiler fuzzing? First, LLMs are too slow. Tools like FastForAll can only generate about 16,000 programs per day, while traditional fuzzers can easily produce millions in one day, making large-scale testing extremely inefficient. Second, the generated code is often invalid or too simple. For example, FastForAll's valid rate is only 37%, and many samples either fail to compile or crash right away, like the buggy example is shown here. Invalid programs get rejected early and rarely reach deeper stages like optimization or code generation. Finally, LLMs struggle on real compilers. Tools like YFox cannot map high-level reasoning to low-level implementation well. To address these issues, we designed LLMs. The core idea is simple. We decouple LLM usage into 2 stages: an offline stage that builds a readable code database using LLM, and an online stage that synthesizes large valid programs without killing the LLM again. On the left, the offline stage collects code from real GitHub projects, lets the LLM generate diverse snippets, then validates them and profiles each one. For example, we got for 1 with 1 as the input and 2 as the output. We also know like y equals to 2 when profiling. On the right, the online stage reuses these functions as Lego blocks, collecting them through function calls or global variables. For example, we try to insert for1 to for2 with the same value at line 4. With each iteration, the program grows more complex and realistic. In short, the offline stage ensures real and valid code generated by LLMs. It fuses with traditional program analysis with LLM understanding to ensure real and high-quality code generation, while the online stage builds deep and interconnected programs at minimal cost without killing LLMs again. Now let's take a closer look at the offline stage, where we aim to generate real-world code with real capacity. Previous LLM-based testing tools often feed a model with simple context, like standard documents or small toy snips, which fail to reflect how real compilers behave in practice. Here, we instead provide real-world codes and meaningful context. So the LLM can reason about the actual program logic, align syntax and semantics, and transform the snippets into compilable and realistic functions. For example, we use the real code from ACC, a small compiler. Then our prompt asks LLM to convert these programs into a unified and compilable format, while preserving their original semantics. This task doesn't require the model to write new code from scratch, but rather to understand, reason, and restructure the existing real-world code, which perfectly fits the strengths of the large language models. Here, it expands the complex structured parameter and replaces the external function with function from ST, which traditional tools find very difficult to do. The key takeaway here is that LLM truly understands code semantics. They can reason, transform, and complete snippets, laying a strong foundation for our offline stage. So after generating these real-world functions, the next step in the offline stage is to make sure they are both valid and reviewable while maximizing the semantics for testing. In total, LegoFast constructs a database of over than 500,000 valid functions. How do we construct it? Let's take that same example before. There's a potential runtime overflow here when writing the body array. To avoid this UB, we automatically validate and provide each LLM transport function using multiple compiler toolchains tools like Sanitizers, like ASIN here. Functions that fail any of these checks are discarded. The remaining valid ones are then provided to get their I/O values and runtime profiles. So, for example, we know that len equals to 1 and analog equals to 2 at the beginning. All provided functions are stored in our reusable code database. Please note that we only construct this once and can freely reuse it later without killing the LLM again. Now let's move on to the online stage, which focuses on building dependencies to increase complexity. LegoFast reuses the validated functions from the database, and first it generates a driver program, a seed with the main function. It calculates and prints a checksum for later differential testing. Then it builds dependency among them through function calls and shared global variables. Once the driver and dependency are ready, we can directly start fuzzing on compilers like GCC and LVM, completed without any LLM involvement. Here's how LegoFast performs iterative program analysis synthesis using what we call function breaks. For example, we want to synthesize the for function into the buffer write. How do we do that? Each function in the database comes with profiling info. For example, for takes input 1 and output 2. Also, for the buffer write, we know that analog equals 2, the same as the output of the for. So we start to replace analog with for. The function for also requires something as an input. So here we got a variable len with the same value as the input. As a result, the synthesizer simply replaces analog with a call to the for. We also added the call of the for to the driver function here to calculate the checksum. This links the two functions through data dependency, keeping the program valid while making it more complex. The second way LegoFast links pieces is with global variables. We have prepared a list of random global variables at first. For example, the g with the value 1 here. Our profiling shows that at this site, len equals to 1, so we simply replace the use of the len with g. Same as before, we use g to mutate the checksum as well. Together with function call insertion, the global sharing enables LegoFast to build large and meaningful test programs. And finally, we print and compare the checksum under different optimization levels to find if there exists any compiler bugs. Finally, let's see how well LegoFast actually works in practice. So far, LegoFast has found 66 bugs, and 56 have already been fixed by compiler maintainers. What's notable here is almost half of them are miscompilations, subtle logic errors that many existing tools completely missed. Some of these bugs are quite important. One of them had existed for over 20 years, and discovery even led to an update in other tools. You can see the maintainers' reaction here. They were surprised that the bug hadn't been caught earlier. Overall, LegoFast can uncover a wide range of issues, from crashes to deep optimization bugs, demonstrating that it's not just theoretical, it really works end-to-end. We also, to better understand how each part of the LegoFast contributes, we performed an evaluation study on its key modules. First, we tested different LLMs, including the legacy models GPT-3.5 and task-specific models like Chain Encoder. The results show that the framework itself has nothing to do with the choice of the LLM. Next, we examined the importance of the database. We found that real-world code plus LLM generation leads to larger and more complex program generations compared to the traditional database like serials. Finally, we studied the impact of the iteration number in synthesis. We found that the best trade-off is when the number equals to 100, which achieves highest coverage on both GCC and LVM. Together, these results confirm that LegoFast design is robust and scalable, independent of the specific models or parameter choices. Finally, we compare LegoFast with several state-of-the-art tools, including generation-based ones like Serial and LLM-based ones like FastWall and YFox. In terms of bug fighting, neither FastWall nor YFox was able to discover any miscompilation bugs, while LegoFast consistently uncovered both crashes and deeper logic issues. For coverage and speed, LegoFast achieved over 50,000 lines of code additional coverage and ran about 146 times faster than those baselines. The example on the left shows one of our synthesized programs It forms a long dependent chain built through multiple iterations, which helps expose complex compiler behaviors that other tools simply miss. To wrap up, LegoFast opens up several promising directions for future work. First, we can explore alternative prompting methods. Second, we can plan to incorporate more sources of code snips, so we can go beyond function level synthesis. And finally, we can go beyond C compiler testing. This brick-by-brick idea doesn't just stop at compilers. It points to a broader future for LLM-driven program synthesis and automated testing. To summarize, LegoFast is a powerful and cost-effective LLM-based framework for compiler testing. It combines two stages: an offline stage that builds real and reusable complexity, and an online stage that's fast, cheap, and completely LLM-free. In real-world testing, LegoFast had already found 66 bugs, with 56 confirmed fixes in GCC and VN. And more importantly, it introduced a new paradigm for LLM-based testing, one that's easy to extend, flexible across models, and highly effective in practice. You can scan here for code and its found bugs. Thank you for listening, and I'm happy to take any questions.
We have some time for questions. I think we can have more than 2-3 questions.
Hi, Harry Goldstein, University at Buffalo. Thank you so much for the talk. This is really cool work. I really like that you're not using the LLM during the key generation loop like Fuzz for All does, for example. Although one thing I did like about Fuzz for All is that they talked about being able to kind of easily adapt to new features of the programming language. Do you know how much, do you have a sense for like whether a new feature that you add maybe 5 to 10 examples of in the database could be represented well enough in the generated test programs? Or do you think you need like quite a bit of data on a particular feature in the database in order to perform well?
Well, thanks for the question. This is also one of our ongoing work, like targeted compiler parsing. Because when a new feature appears, you need like a certain structure. Like if you want to test like loop analysis optimization parts, and you would search for the code with like multiple loops. So in our database, you can modify this database to equip the code snips with more features. Like you will count how many loops does the code has, or you can also use like OPT to check if it trigger a certain optimization path. So in that way, I think LegoFast is easy to extend to other features or even other languages, or like you can make it to a targeted compiler parsing framework. Yeah, thanks for the question again.
Great, thank you.
And also the other person who would like to ask a question.
So I was curious, were the generated test cases really long, or did you notice that they're like the test cases that found bugs? Did you notice that there was a trend where they tended to be really huge and complex, where they had to do kind of post-processing to do test case reduction, or were they pretty concise and like targeted toward the bug that they uncovered? Oh,
thanks for the question. The answer would be this is huge, because you can see the best iteration number is 100, and that would produce around like 8,000 lines of code. And when a bug is detected, we use like C-reduce to reduce the whole program to find the real buggy program. And the average of the real buggy program is around like 20 or 30 lines. Yeah, that's the answer. Yeah.
Cool.
Thank you.
Hi, I have a quick question for the, I'm curious which components contribute more to the performance. For instance, the seed augmentation or the seed composition. So which component contributes more to the maybe coverage or bug finding?
You mean the components of the LegoFast?
Yeah.
Yeah, I think the database construction contributes the most, because like you really utilize the complexity from the real code, and that triggers like more deeper compiler paths. Yeah.
Okay, so what if I only use the seed, the database augmented by a larger model and use, general mutation strategies. Is there such evaluation study?
Yeah, we actually did that experiment.
Okay.
You can check it on, in our first RQ because we use the individual functions to test if we can find any compiler bugs. And for we have tested for a week and no compiler bugs was found. Yeah.
Thank you.
Thank you.
Thank you. I think